Okay, hello everyone. Let's go ahead and take a look at the next section, which is called curve properties. And we're going to take this into two parts, and we're going to just take a look at part one for today. Now, what I mentioned to you at the beginning of this chapter is that one of the basic applications of differential calculus is to be able to analyze functions. And so what we're going to do is we're going to take a look at how we can apply calculus to analyze a particular function. Let's go ahead and take a look at, say for example, this function here, f of x is equal to x to the third minus 3x plus 4. Now, what does that function look like? Not exactly sure. Calculus is actually going to give you a way by which you can determine a reasonable graph of this function without having to plot an infinite amount of points. Okay? So let's go at it. Let's see how we can do this, and let's see how we can apply calculus to help us do this. So the point is, let's graph this function. Now, we can of course use some of the other techniques that we have and some of the other information that we know that will help us to actually find certain important values for this function. For example, here's all the non-calculus related items. The domain. What is the domain? Well, we know that the domain is going to be x cubed minus 3x plus 4, so there's no restrictions, so we know that the domain is all real numbers. Now, just by looking at the function, can we actually go ahead and tell what the range is? And at this point, no. Do we know what the x-intercept is? Well, if I let f of x be equal to 0, I don't know how to go about factoring that, so I don't even know if there's any x-intercepts. Do I know what the y-intercept is? Well, the y-intercept, if we let x be equal to 0, f of 0 is just going to be 4. So I know that this will be, let's put that in red. I know that will be the y-intercept. Okay, and I'll put it right here. Here you go. I know that that point exists on the graph. Now, some of the other things, I know that this is a cubic function. So if I think about what the cubic function looked like, the cubic function, the parent function, looks something like this, right? Now, does it look something like that? I'm not exactly sure. Okay, so let's go ahead and think about how we want to use calculus now. Now that we've exhausted all of our non-calculus options, let's look at calculus to help us plot, or help us get a reasonable approximation of this graph. So, here we go. Take the first derivative. If we take the first derivative of this function here, I come out with 3x squared minus 3. Now if I look at this, hey, I can factor that. I can factor out the 3 first, and then after that this x squared minus 1 can be factored to x plus 1, x minus 1. Now that we have that, now we can actually go ahead and use some of the results that we can have if we go ahead and consider the first derivative. Now, here are the first derivative results. It says that f prime of x, if it is equal to 0, this means that f of x is stationary. Okay? If f prime of x is greater than 0, this means that f of x is increasing. If f of x is less than 0, that's going to mean that f of x is decreasing. Okay, so again, what we're doing is we're taking a look at the first derivative, and the most important thing is we're going to look at its sign value. Just like we did with the motion graphs, we looked at the sign value of the velocity. Okay, so we're going to just focus on the sign values. And when I go ahead and take a look at this, the easiest one to go ahead and actually look for is when the derivative, the first derivative, is actually equal to 0. If we can figure out where the derivative is equal to 0, then that means that everything else is either going to be greater than 0 or less than 0. So let's first determine where f prime of x is equal to 0. So we have a factored form, and that's why we've been practicing our factored form. If f prime of x is equal to 0, then I know that this 3 times by x plus 1, x minus 1 is also going to be equal to 0. If I go ahead and solve for x, x is going to be equal to negative 1, or x is going to be equal to 1. So what that means then is that when x is going to be equal to negative 1 or 1, the function is actually going to have a stationary point there. Okay? Now, I don't know where that point is, but I know that for when x is equal to -1 and when x is equal to 0, the value is 0. So I'm going to just put a value here and put another value there. Okay, now I'm going to just say that that's going to represent where the first derivative is actually equal to 0.